Hi Professor Caps, welcome to balloon geometry. Not quite an experiment, but it was an experience. I've created 5 balloon models that represent the electron domains, creating an electron geometry. And we're going to go through them all one by one, but basically I wanted to go over why they form. And what I learned was that this phenomenon is based on valence shell electron pair repulsion, which basically states that electrons will assume a position around their atoms in the farthest possible distance apart that they can get. So, for instance, starting with the linear forms, there's usually a central atom and then the 2 other atoms, and they generally form a linear formation because the 2 electrons circling will get as far apart as away from each other as they can, which creates a 180-degree angle. The next is the trigonal planar, and it is a 3-electron domain. So 3 electrons represented by the balloons in their domains, and normally it would stand up like this. Oh, look, I almost got it. So, because they, again, try to get as far away as they can from each other. So they will stack up and repulse each other and then assume that form. If you were to create, instead of a 3 atoms around a central atom, if you only had the 2, you wouldn't see this one. It would be invisible as a lone pair, and you would have a bent molecular geometry with 1 lone pair. If you had 2 lone pairs, it would be linear, which I guess that would then become the central atom, and it would form a linear geometry. Okay, moving on. The tetrahedrals are a molecule type AB4. They contain 4 electron domains. And normally, I want to look at this real quick, they form a tetrahedral. So their angles are in space actually going to be 109.5 with their angles, and normally they would set up like this. I don't know if they'll set up like that, but that's how they should set up. And if you were to remove one of the atoms, leaving 3, but still having a lone pair to create that 4-electron domain, you would get a trigonal pyramid as your molecular geometry, and it would look something like that, with the lone pair pushing the rest as far apart as possible to create that shape. If you were to still have 4 electron domains but only 2 atoms, you would get these 2 would become invisible as lone pairs but still do their job to push, and you would get a bent representation as a molecule geometry. Trigonal pyramidal is next. That's the one that has 5 electron domains. So 5 balloons representing the electrons circulating around the molecule. And if there was a central atom, they would set up in a shape sort of like this. I don't know if they'll stay, but kind of assuming their own shape. The balloons are sort of repulsing each other just like the electrons would. I think that's what our model is supposed to do. Tying these together was a little tricky, and I think that because they're so short, they're not able to assume the position that they would normally if you had a nice long balloon cord. So trigonal bipyramidal has 5 electron domains. One of the examples is PF5. If you took away one of these atoms and left yourself with 4 atoms and a lone pair, you would get a seesaw geometry which looks like that, sort of, I think. Where two are supposed to be opposite of each other, and then two set up like a seesaw. If you were to take away another one atom, and you were left with three atoms and two lone pairs, you would get a T shape. So you would get something like that. Where they would be, these two would be straight across in the equatorial line, and then this one would be straight up. It goes on to say that it could have a 3 lone pairs and it would be linear, but I don't know if I can do that without popping all the balloons. The last one is the octahedral. Its molecule type is 86 if it was just in the electron domain geometry, but regardless, it contains 6 electron domains. An example would be sulfur fluoride 6. I'm probably not saying that right, but it looks like an octahedral. So in space, it would take up a octahedral shape. I don't know if it will do it on this, but what I did learn that if you remove one of the molecules and you have one lone pair, it'll do a square planar where, 2 lone pairs, it'll do a square planar that looks like that. Otherwise, it looks like a pyramidal one. So if you took this one away, it would stand up kind of like that. So, but it won't stand up by itself. 2 lone pairs would be a square planar that would look like that. And the pyramid, again, I'm not popping them. So I found a chart that made a lot more sense to me than the book chart did. It's organized a little bit better with how it breaks down into the different angles and the different molecular geometries with how the lone pairs fit in. And so I'll attach all of that with my video. And thanks for watching.